So trading like officially is a thing.
Yeah.
I deal with trading.
I don't put these.
That's something to actually work together.
Okay, after this, I have to make sure that feels safe. Or at least like to, because I don't know what's working.
Reactive power for resistance. No, I got like gigawatts, like a 10 resistor. Yeah. Brother, sorry, into the negative. No, because it was a kilovolts times kiloamp.
Yeah, that would work.
I know, but it's a common resistor that doesn't transfer. No, the 3 ohm. It was a 3 ohm. That's what I thought.
I just don't feel it.
Okay, so let's start by attendance. So we're almost done with this chapter. I'd just like to go over a couple topics very fast, and then we'll start with chapter 3 today. So, what we were talking about last time? we were discussing the different types of connections in the three-phase balanced circuits. Okay? And now we are here. We will go over the advantages of balanced three-phase circuits versus the single-phase ones. And we'll talk a little bit about energy conversion, but those topics actually are quite related for another course. If you take in the future power electronics or drives, they would be covered there. We do power systems here. So what are the advantages of the balanced three-phase system? Can anyone tell me? I think we went over them before. No thoughts? What?
You can get more overall average power out of it. Three-phase system.
Yeah, definitely you'll get more. You're getting 3 times even. But there's something related to the cost. Is there any savings by using three-phase systems over the single phase in capital cost? You are having three-phase system, which is 3 multiples of the single phase. But there's something where we are saving a lot. And this is the advantage. What?
Less wires.
Yeah, this is true. What we are missing in the three-phase, or what's the advantage of the three-phase system? Excellent. Yeah, this is the point. You are avoiding having 3 neutral wires for 3 single-phase connections. So you're having just a single one. Okay, Charlie. I look by the end for all the attendance of MSU. This is one advantage. Here they have explained that in details how we are saving over that physical connections from single to three-phase systems. So you could see the difference between the two. The other thing is that for when we are comparing the delta with the star connection could have an advantage by having that neutral wire, so that in case you have any over transient or over voltage, it could have a path to get out of the system, while in the delta connections you cannot have it. One more thing, it's related here. The second advantage would be is that the total instantaneous power in the three-phase system, it came out to be constant. It does not have a time component. This is a very big advantage in comparison with the single phase, which had a time component. Okay, I hope people could remember that information. Because if you go here and you read what's going on, they would say the average power is constant over the three-phase system, which means if you are running a motor, that there'll be much less noise, much less fluctuation in the system itself because of that average power. While if you are running a single-phase system, you will feel that fluctuations. So that's why in most of all the big machines, they have three-phase systems. They don't want to have that fluctuation every instant. So they get into that three-phase system to ensure a constant supply of power all over the time. I think those are the 2 big advantages of the three-phase system over the single-phase one. And here there are some explanation over those. They go in detail, like as in the equation, PA has 2 components, a constant and double frequency solenoid. I'm not reading all those, but we have covered them before. So we just need to know those 2 advantages out of this section. For energy conversion, can you list for me a few types of energy conversion schemes? If no one is sharing, I would start calling names. Let's start with MSU people this time. Justin, what do you think from MSU?
Are you talking about like delta to Y conversions?
No, I'm talking about the forms of energy conversion in general.
Oh,
What could be a form which could come to your mind to generate electricity from that? Like fuel. Fuel is a one form where you convert the fuel into energy or power
Oh, I see what you're saying.
in the plant. What could be another type?
Solar?
Solar. Yeah, this is good. You're converting the light into power through the solar panels. Okay. Jonathan from MSU, what do you think? Is there any other type on your mind? I think Jonathan cannot hear us.
I said his mic is broken, but he's in the chat.
Okay, yeah, probably he's saying something. Okay, wind, yeah, definitely. The wind turbines, it's another form. Hydro generation. Water could be used in thermal generation to get some power. So those are all non-fundamental electric sources of power generation or power conversion. That applies also to nuclear. Here, when we talk about electric energy conversion, about electricity, it deals more with electricity conversion from one form to another. So I think every one of us is aware about the AC and DC systems, okay? Those should be covered in electric circuits. So when we talk about electricity energy conversion, we are just moving from one form of those into another, from AC to AC, AC to DC, DC to AC, and DC to DC. Okay? We are within this small loop. I'm not involving here or everything in every other type of electricity production or so. So we talked about the non-electric to electric energy conversion, and few of you listed few types: fuel, wind, hydro, nuclear, solar. Okay, this is non-electric to electric energy conversion. The electric to non-electric could be reversed. Like, who could tell me that process? Okay. Actually, the generator and the motor, they are just the same machine but being reversed. Okay? They act in that manner. So one of them makes electric into mechanical energy, which is the motor, definitely. And the other one makes the mechanical energy into electric energy, which is the generator. Who's still taking electromechanicals this semester? Who's taking that course? Only 2? Should be more. 3? Okay. So those would be covered in that course. They cover all those type of machines. Now we'll talk a little bit about those 4 forms. As I've said, they should be covered in other courses, but we'll go through them pretty fast. So I mentioned those 4 type of conversions. So form 1, AC to DC. Who could give me an example of that? From AC power to DC. Yeah, rectifiers, like your power supply devices, chargers. You're getting AC current from the connections, and then you pull that into your phones to be DC power because you have a battery there. It cannot get AC power. This rectification process is quite a power electronic processes that should be covered there. But we need to know that that type of electricity conversion falls under that domain. What about DC to AC? Yeah. Yeah.
Solar panels.
Exactly. Yeah. Actually, my family yesterday has installed a solar system for the house. They got 8 large panels and a lithium battery, and they got an inverter to change that electricity from DC into AC, because the panels and the battery would be DC supply, but we definitely need AC in the house. So this is a typical type of thing to use, that electricity conversion. DC to DC. DC to DC conversion. Yeah.
or buck converters.
Okay. Okay. Did you take power electronics?
No, I did a lot of stuff.
Okay.
Yeah.
I did my master's. It was about power electronics, so I'm aware about those. So typically you have DC voltage now, and you need to have another level of DC voltage. So it's either buck, where you reduce your voltage. Let's say I have 10. I want my voltage to be 5 for certain device. So I use buck. I have the boost, which is boosting the voltage from 10 to 20 or 10 to 15, depending how efficient is a boosting device and if it's capable. There's certain limits. You cannot boost 1 volt to 100, let's say. This can't happen. The law of physics do not apply. And there's buck boost. That device could operate on both directions. I was doing some research at the time about the dual inverter drive, which have two components, two converters attached to each other. So anyhow, this is a typical example of DC to DC conversion. AC to AC, variable frequency transformation. Here you have your AC voltage, but you need another AC level. You cannot use that converter. That item won't work. It's a DC component. It needs DC voltage. So there's something called the variable frequency drives. Those are in power electronics, where they make a collection of devices, and that structure would be able to translate the AC voltage from one form to another. Another way to make the transformation, but that won't be a variable frequency probably, is the transformer, the famous transformer, okay? Because we are just changing the voltage from one level to another, but it's still AC. So I think this is all what we need to know from this section. Here's some example. Single phase inverter. Yeah, I used to draw those on MATLAB and things like that. And I do controls of a much bigger, it's called PWM techniques, stuff like that. For the three-phase inverters, it's like this 1 times 3. So you need to do much more work. This is a variable frequency drive where you have all those components. This is the input power. This here should be the output. And here's the conversion process with all those devices interconnected. Okay, so we're done with this chapter. So the problems which I've shared with you for assignment 1, I had an office hour today. I had a few people joining, but I'm receiving quite general questions. It seems that everyone is doing well on the homework, because I did not hear anything today about that. So it seems people are doing well on the assignment. So let's see how's that going on. So I've listed a number of questions here from this book. Be aware those are problems. If you are trying to use a prior version, they have exercises and they have problems with the same numbers. We are doing problems. In this version, in our class version, it's all problems. You'll not be lost. Okay? So be aware, people who are using previous versions, I do not endorse them. I tried to get the same exact questions with no modifications between both versions. I had to go through 55 questions in the chapter to do so, and to make sure that those questions are good enough for you, covering everything in the large chapter that we covered. So typically, if you read the problem 2.12, you should go here to 2.12. This should be what you'll be solving. Okay? I'm not responsible if someone is using version 3, let's say, and I'm using version 7. This is something beyond my means to control. As I've said, there's a book in the library. You could access that. If you are really lost, you can contact me to check if those are your questions. Other than that, the previous version is very similar to this one. So I just wanted to make sure that everyone is going to the problems section. I still highly encourage you to use this version that we are using right now so that you don't get missed or lost somewhere or solving another question. Because the other exercises are very simple. I would not even ask. I will not comment now about the homework until I see your performance. I had a meeting with the grader. I gave him some directions today, actually. He will start immediately grading your homeworks on Monday, right after the submission. So let's see what would you do, and we'll talk about the homework later. If in any case, if I see like there's certain problems where the majority of us are not able to solve, we can do them here in class. But first, now I will not comment about them until I see your performance. A few of you with the accommodation requests, I received them from SNT and MSU. I filled in them yesterday, so you should be okay. I don't know if you get notified by them. So I was just letting everyone now know. One more comment or announcement. The department nominated me and Dr. Huang to make some promotion for the incoming graduate students or applicants. And we made some interviews with them, some recordings, video recordings and stuff like that. And we went over the labs for me and Dr. Huang. And they still would like to take some pictures of us here on Friday. That won't impact you in any way. I think that a photographer will be right there just taking images for me, typically, and you'll be like in the here. Maybe your heads will be in the photo. So I'm just letting you know ahead of time, so you don't get surprised. Like, who's that person? What he's doing? It's just some department promotion, and they'd like to do it, so I accepted that. And we'll have another work with Dr. Huang regarding that thing later. So now, is there any question before I move for chapter 3? No questions? MSU people? I don't know, by the way, what you have in your library in the university, if you have the book or not. So let me know if you run into any problem. But you can still use that free version because we chose the same questions. So I think I'm done with this chapter. So I'll move for chapter 3. Power transformers. I've already uploaded the slides over the weekend. So I'll show them to you now. If you go to your Canvas page, you should see now chapter 3, okay? I've worked a little bit on those. You could have a look at that information. As I've said, we do a lot of calculations here. It's impossible to me to write down all those examples and calculations and derivations in the slides. I would need like 1,000 slides for each chapter. So typically here in the PowerPoints, we make a summary of the things that we need to know and of the formulas, but you still need to use a book if you'd like to cover everything, okay? Yeah, and make sure to utilize the recordings in case you are missing some calculations, because I have to do them. Actually, I'm on a race with time to make sure I'll be covering everything for each lecture. So if you missed anything, just open the recording, check the that page so you'll be able to see what's going on or what you have missed. Okay, power transformers. What are they? Okay, good. Why they are called power transformers, not just transformers? Are there other types of transformers? Yeah,
They're usually used for like much higher voltages.
good, good. There are other units for like measurement transformers or other units. They are very small. They are actually just for sensing. They are not for power conversion. So here we are talking about those large units in substations, where typically they would receive, let's say here in the US, a typical voltage is 110. But if I'm generating somewhere far in Arizona, they have a lot of solar panels and stuff like that there. So let's say the generated voltage was around 4,000 volts. Because I don't know if you took any solar class or renewables, but I took one when I was undergrad. They have all those solar panels connected in series and parallel. And those lead to the add up of voltage and current. Okay? Eventually, if you have a very large network of solar panels all interconnected, they will deliver a very high voltage, okay, and a very high current. So the series and parallel connections, they determine whether voltage is additive or current is additive. Anyhow, those are background information, not related to transformers. So let's say they did that in Arizona. They got a 4,000 volt voltage out of that solar plant system. And they had really good transmission lines, overhead, high voltage DC. And they transported all that power to this state, okay? So they arrived here about 3,990 volts, okay? Eventually, we cannot really dump all that voltage here on town. Everything will burn out, probably. It'll be like an over voltage. It's like a strike or so. So they'll have a substation somewhere here in the suburbs. That substations will have very large transformers like those, where they will try to take down this voltage from 3,990 into 110. Hopefully, that would happen. And then your power is ready to be dispersed over the neighborhoods and so. So typically, they use those units in such situations. There are different types of them: oil, forced coil. I don't know. I don't care actually how they are made up. Their structure is changing a lot nowadays. They're trying to use the best materials, the best for conductivity, and the best for insulation. We're not into their design. We'd like to know how they work, typically. So here they are trying to say that we have like ultra high voltage transformers. We're typically talking in very high ratings, 1,100 kilovolt, 1,200 kilovolt ranges, very high. So the typical need is that they cost us actually, they are providing a lot of savings for us, those large transformers, because if I'd like to transfer those 4,000 volts from California to here on that level, or if I cannot boost it to that level, if I'd like to get that power from Arizona to here on 110, I'll have massive losses during transportation or transmission. So boosting the voltage to a high level would eliminate or reduce the losses over the transmission lines too much. But then eventually I need to get down to 110. So this is the main benefit of using those elements. Here there are some cases if you'd like to study more or learn more about transformers history and how they're made. But typically, when I took that class in the same book,
We can't hear you.
See. What about now?
Yeah, that's better.
Okay. There's quite a close link between transformers and magnetics. Okay, so we'll start now with the ideal transformer, but we'll make some revision about magnetics because they are closely related. Okay, the concepts are closely related. Although those, I think they are covered in the electromechanics class. Whoever took that class before, not necessarily now. 2, 3, that's it. I thought it's shared between everyone here. Like, I expect like 30 people or 40 will be there. Okay. Well, anyhow, I'll be explaining that. So I expected that to be covered in that class because I'm aware of that content. But if you did not take it, we'll cover it here. So there's no issue. Let's go to do some magnetics now. Here we're trying to implement the transformer windings into a magnet, okay? So we have a magnetic core that you could see here, and we have two windings. Let's say, I don't like to say now primary, but this is on this side, on E1. Let's say this is a loop of wire connected there. And the secondary one or the second one is on winding 2 side, where you see another loop of wire connected there. And this is the magnet core. That's square with some hole inside. I don't know. It's like it's a square of magnetic core. Okay. So effectively, we are trying to apply certain voltage on the first winding on E1. Then the current starts to traverse through the wire. At the same time, that would lead to the generation of certain flux, phi C. The flux should be confined within the magnetic core. I'm saying confined because this is an ideal transformer, which means all the flux being generated will be just in the core, nothing going outside. And we have the magnetic intensity of the core itself, regardless of the transmission. There's certain characteristic for the magnetic material. It's that HC of the core. And then from the other side, you see a generated voltage actually coming out, which is E2. And a current will start to traverse through the loop, which is I2, which is going out of the circuit. Okay? And here you have the core permeability, mu C, the core cross-sectional area, this rectangle, which you see the cross-sectional area of the core, and the mean length of the core, this dotted line. If you can see that, it's like the average length of the core, if you'd like to measure. So you don't take the length, this inner square, nor the outer square. We take the one in the middle. So let's say if I tell you the cross-sectional area is 4, and it's like a squared shape, so that means each side is 2. So this is 2 here. And then you know that this line here is at 0.5, okay? So if this inner square is 8, so this the length of this will be 10. And then LC will be 40 because this dotted line should be a square. Okay? Normally, I will not ask you such questions, but in case you need to do some calculations, you need to figure out those values. Other things related to the magnetic materials will be given for calculations. So here are some characteristics of this ideal transformer. The windings have zero resistance. Those two windings are superconductive, even better than the copper. No loss at all. I squared R is equal to 0. The core permeability is infinite, which corresponds to 0 core reluctance. Here, in this core, there's also no loss. All the flux is traversing, nothing resisting the flux from going through. So it's a very good This is why it's called ideal, because there's no loss at all anywhere. There's no leakage flux, which means the entire phi of C is confined to the core and the links between both windings. So all this flux is within here, nothing going out, and no core losses. So a schematic presentation of this two-winding transformer is shown in figure 3.2. This is a schematic representation of what we said. E1, E2. This is the N of terms that we have, N1, N2. If those are the same, it will be just N. Actually, we'll be doing nothing. So the same voltages will be on the both sides. This is A, T, which is called the turns ratio. That's the ratio of transformation between one side and another. So let's say if A is 10, then N1 over N2 would be equal to 10. So N1 equal 10, N2. Typically, we would have N1 given, so we are more concerned about N2. Okay? And here's some more math over the equations. So that I, here we are trying to make some analogy between the current laws, the U equal Ri, and the magnetics, okay? Between Ohm's law and those magnetics. So here we see Ampere's law is saying that the current enclosed, which is going in this circuit everywhere, should be equal to the integral of H, the magnetic intensity, over that dl, which is the length. Okay? LC. So this is from the law of physics. And here you have this circle, which means all over the range. So if we expand that equation, we'll get this one. HCLC would equal to be to Ni I1 minus N2 I2. In case this value is 0, so when HCLC is equal to 0, then N1 I1 is equal to N2 I2, and that would act as an ideal transformer. Okay? This is an extreme case. It does not normally happen. So here we are saying that the net currents, but after multiplying by the N terms, is equal to the multiplication of the intensity times the length. There's a lot of math behind those equations and how they came from, but even in this book, they don't show us because it's not an electromagnetics course. Okay? And then we need to define the flux, or magnetic flux density, B, which relates mu to H, okay, by multiplying them. So the flux acts like the current in the equation U equal Ri. The flux is acting like the current and that magnet, within the magnet. So if we go over the equation now, N1 I1 minus N2 I2 would be equal to this by substitution of the items. And then you put the values that we got from here, from this one and this one. Like you put B in its terms here, and the phi, and you put that in this equation. So you'll obtain this form. So as I have said, this is the goal, to have N1 I1 equal N2 I2, which means this should be 0. In which case this would be 0. One, this term could be 0. I need flux. Let's agree that phi would have a value. Don't tell me this should be 0. This is different. Okay? Let's think about it. The second term should be 0 now. Can I make the length 0? Is it like okay to have the length of the core or non-existing?
Would it just mean that there's no hole in the transformer?
it means there's no magnet at all if this is 0. And the area must be found because this is a physical device. So the only term I can play with is this mu, the permeability. This is the only term I can play with to get an ideal transformer. I have to make this as high as possible to infinity so that this term turns to be 0. Okay? And this is why this is called ideal transformer. So if we take all those values here, we could define them as reluctance. They are called RC reluctance. So N1I1 minus N2I2 is equal to the reluctance times phi. And here's the equation. So actually, this difference could be defined into magneto-magnetic force, magnet-motive force, MMF, which is N1I1 minus N2I2, and it's equal to the reluctance times the core flux. Okay? The reluctance here acts like as a resistance. It's trying to impede the establishment of flux in the magnetic circuit. So the flux acts here like the current. So I'm trying to give those examples so that people would understand the difference. For an ideal transformer, this mu should be assumed infinite, which means RC is 0, definitely. If this is very large value, this RC would be 0. And here we put RC 0, then we have N1I1 equal N2I2. So yeah, here there's something. Whenever we have currents, we will induce voltages, okay? And the same applies. If I apply a voltage, I could get current. So those are related to the VI relationships and Ohm's law and stuff like that. But there's something, do you know the dot notation, people? Did you take that before? Which means whether those two sides are in phase or not. From what we see here, it means that those two are in phase. But if that dot was below here, it means those two sides are out of phase, which means there are 180 degrees difference between the two sides. Okay? So let's get here. So I explained this in phase and out of phase. Now, Faraday's law. It states that the voltage induced across n turns winding by a time-varying flux in the winding is equal to this value. So here it seems to be that whenever that flux starts to be generated, it will induce some voltage again. And that process keeps going on. And this value of the generated voltage or induced voltage is equal to N d phi by dt. Okay? It's something similar to V equal L di by dt. Okay? If people know about inductors and stuff like that. I'm just giving here as an example. It does not necessarily mean this is equivalent. Okay? This is just an analogy. Because the I acts like a phi and this V acts like this E. But this E value is defined by a steady state flux with constant frequency and representation of ET and phi t by their phasors E and phi becomes like that. Okay, so this is another representation for the voltage in terms of frequency and number of turns and flux. For this ideal transformer, the entire flux is assumed to be within the core, linking both windings. So if we translate that for both sides, those terms apply for E1 and E2 on both sides of the transformer. Then, if we divide those equations by each other, So if we divide those equations by each other, we will get rid of j omega phi c. We will just have actually E1 over E2 equal to N1 by N2. Fair. We know that because the voltage ratios should be equivalent to the turns ratios. You can play with the equation, like to put N here and I there, it won't affect anything. This is what he's doing. We talked about the polarities and in phase and out of phase. So we will call AT as turns ratio, and it's equal to N1 by N2. And then we can define actually E1 in terms of A. Instead of putting N1 over N2, we'll just use that form. Now, if we substitute the equations in terms of I, we'll get an equivalent form, but be aware. Here the things are reversed. I2 should be equal to AT I1. It's inversely to the voltage, okay? So I1 would be equal to I2 over AT. And this is what he got there. Because voltage and current are quite inverse to each other. They cannot follow the same way. The same applies for the complex power. And we've explained what's the complex power. Now we'll move forward with that, but we're just using it here to see how much will be S1 and S2. S1 is VI star, which is I1 star. S2 is E2, E2, I2 star. But S1 must be equal to S2 because this is an ideal transformer. Okay? And this is what he's doing here. So if S1 is equal to E1 I star, E1 is equal to AT E2, and I1 is equal to I2 over AT, and then with the star, you'll get rid of the AT from both sides. Okay? They'll cancel. And you'll just have E2 I2 star. Which means the complex power is conserved in this ideal transformer. No matter what happens with I and E, S is still the same on both sides. What about Z, the impedance? Z1 is equal to E1 over I1, and Z2 is equal to E2 over I2. If you put the equivalent values of E1 and I1, you will realize that we could divide Z1 by Z2, and we'll get a proportion of that regarding each other. But here we have two ratios being divided, so they will multiply. So instead of having N1 over N2, we'll have that value squared. Okay? This is important because it means that the ratio impedances are squared, unlike the current and voltage ratios. So here's an example. An ideal single-phase two-phase winding transformer has those ratings 20 kVA, which is the S. Those are the voltage ratings, 480, 120, primary, secondary, okay? 60 hertz frequency. And then you have a source. So let's say this is the transformer. This is how they typically represent it. And you have here a source, and you have here a load. I'm very bad in drawing, but anyhow. So there's certain power flow going through from the source to the load through the transformer. You have those ratings. Having 480, 120 can give us the ratio. Okay, so what would be the ratio here, the AT? It will be 4 dividing 480 by 120. That does not mean I must have a voltage source here of 480 and here 120. I could throw here a voltage of 400 and equivalent ratio will be here of the voltage, okay, by this factor. So I could get here 100 voltage, okay? It's not a must to have here 480 because the transformer is 480 volts. So he's saying calculate the following: the voltage across the 480 winding, the voltage here. I was given that I have a load connected to the 120 volt winding. The load absorbs 150 kVA, which is S, is given, and the power factor. From those, I can obtain S and the angle. The angle is the cosine inverse of the power factor. So you will be getting, at first, E2 is 118 because it's the delivered voltage, load voltage, 118. And then you will get the turns ratio that you got. E1 is 80 E2. It came out to be 472. That's what I was saying. It may not be 480. This is the circuit representation. Then the complex power, S2, it should be equal to S1. And you have the 118 and the I2 star. So S is equal to 15,000, the given one, cosine inverse to get the power factor. So you get S2. So you divide this value by the 118 volt because it's given, the output voltage. So you get I2 star. You invert the angle, so you get I2. And those were given. So you make the calculation by S equal VI star. So you get this I value. Those are given. Okay? And then the load impedance, Z2 is equal to E2 over I2. Those two are given now. 118 over this value. So it's 0.92 with this angle. And then get the load impedance referred to the primary winding, the 480. You have to say that we need to apply this turns ratio, but multiplying by the square. So you multiply that by 4 square instead of 4. Okay, so you obtain this value on the primary side, on this one, although you started with the secondary, with Z2. Okay? And then for D, I forgot the question, the real and the reactive power supplied. So now we are here on the other side. And we have said that S1 is equal to S2, and we got the value. So you change from the phasor to the rectangular form, and then this would be P, and this would be Q for the active and reactive powers. So I think I'm done with this question. Where's that MSG? And see you on Friday.
Yes. Yeah. I've written first part of it. I can write the rest of it if that's fine, or someone else has to write it. I don't really really matters, does it?
Yeah, no, I don't matter.
Okay.
I was just thinking if we wanted to do like one person a week.
Yeah, that works. So I wrote the first part of it. So I'm gonna just write the rest of it. Do 2 weeks to it, right?
Yeah.
Okay. Well, I'll try to get it. Lab on
Yeah.
You too.